Hello, my name is Valentyn Domanskyi, and today I would like to present our research about regression-based method for real-time solar power plant efficiency forecasting. Authors are Myroslav, Komar, Khrystyna, Lipianina-Honcharenko, Valentyn Domanskyi, and Nazar Melnyk. So, with the current popularity of green energy, solar power plants have become one of the leading renewable sources, and it's because they have a fairly low cost, they are easy to operate, and they have high durability and reliability. And due to a large number of external factors, the efficiency of solar power plants is quite unpredictable. So those factors include the weather condition, the geographical position of the solar power plants, and their operational conditions, and also the sun position. So it is an important task to introduce systems for forecasting the generated electricity for more efficient energy management. Currently, there are a large number of models and methods for predicting the efficiency of solar power plants, and depending on the duration of forecasts, forecasting can be divided into very short-term forecasting for less than 30 minutes, short-term forecasting for less than 1 hour, intraday forecasting for like 8 or 6 hours, medium-term forecasting for 1 day, and long-term forecasting from 1 day to months or even a year. And depending on the required forecasting horizons and the available data, the required forecasting method might differ, and the methods can be divided into the following: the artificial neural networks, the time series forecasting methods, the machine learning methods, physical and statistical models, Ansible methods, and nowcasting. But today we wouldn't focus on their pros, cons, and typical sphere of usage, and only want to mention that one of the research objectives is to predict online performance, which is adjusted by updating weather indicators. So therefore it was decided to use the regression models for forecasting because they are faster than neural networks and their input data can be variable. So the object of our research is solar power plants and their operation under various weather and operational conditions. The subject of our research is development and analysis of regression models for forecasting the efficiency of solar power plants. And the novelty of our research is on the development of a methodology that integrates external factors such as weather conditions and the condition of solar power panels directly into the forecasting model. So for our research we used the dataset which consists of the operational data from solar power plant in Zeleny village, the Ternopil region of Ukraine. We used the data period of the 4 years with the granularity of 1 hour, and to this data we attached the weather data from OpenMetal and SoCast APIs, and also the sun position data from SoCast API and SunCalc library. So as I previously mentioned, there is a pretty large number of variables that affect the efficiency of solar power plants. So we made a literature research to select the most influential one, and the literature research showed that the weather conditions as air temperature, humidity, atmospheric pressure, wind speed, cloudiness, cloud transparency, direct and scattered solar radiation, and also the sun position, like the sun's zenith, azimuth, and altitude have the highest impact on the efficiency of solar power plant. And to check this hypothesis, we built the correlation matrix that shows the correlation between the variables and between the weather variables and solar power plant efficiency. To test our regression model, we used the QRT matrix of mean squared error, the mean absolute error, and the mean absolute percentage error. And the forecast and the actual forecasting was built in multiple stages. So firstly, we used the in-quartile range method to identify and remove the outliers. Then we split the data into the training and test networks. So as a training set, we used the data from the first 3 years, and a test set we used the data from the last year. Then we added the additional time identifiers as hour, day, and quarter to our test dataset, and and then we used several regression models on our training data set and used them from the third power plant efficiency of forecasting, and then we selected the model with the best result and modified its parameters with the grid search CV function, and based on the best of the selected gradient boosting regression models, the forecasting was performed. And we received the next clarity indicators, and also on the graph you can see the comparison of the real data with data that we received from our regression model. So then we added the future timestamps and time features to the future period, and based on which the forecasting was performed. And on the graph you can see the real data and the data that we received from our model. So in the results, using the gradient boosting regression model, we obtained fairly accurate forecasting results, and larger deviations in the winter are explained by the shorter daylight hours when the panels are in operation, and also by the fact that the snow is covering the surface of the solar panels, which also affects their efficiency. And other researchers have also noted similar deviations in their work. In the conclusions, we might say that research underscores the importance of accurate and real-time efficiency predictions for solar power plants, which face variability due to external factors like weather conditions and the physical characteristics of solar panels. Research presents a novel method for real-time forecasting of solar power plant efficiency, leveraging regression models to predict performance based on historical weather data and the solar power plant's operational data. The gradient boosting regressor emerged as the most effective model, enabling more efficient integration of solar power into smart grid systems and optimizing energy management practices. And comprehensive data normalization and testing of several regression models offer valuable insights into the critical role of weather indicators and solar power panel positioning in solar power generation. The future research should focus on addressing challenges such as seasonal variations and external factors like snow coverage to further refine predictive capabilities. Thank you for your attention.